Isn't this a great venue? Several of us were talking that this is the nicest hotel we've ever stayed in, ever, which is probably, out of the people I talked to, that's a cumulative 1,000 people years of traveling. You're going to hear some differences of opinion on the details here. I've noticed already based on the talks during the breakfast, but I think the people here that will be speaking are unified in one basic message, and that is there is no climate crisis, there is no climate emergency. Okay, we're in agreement on that, but we can argue about the details. Sometimes it's hard to get your hands around the climate subject, global warming, climate change, what we should do about energy policy. There's a lot of weeds you can get into, okay? And so a lot of people just throw up their hands and they go along with whatever the scientific consensus is or what the policy consensus is or whatever Al Gore says. So I'd like to give you some advice to hopefully make things a little easier. Try to think of all of the talks that are given today as something that's in one of three categories. There's sort of three categories of issues that we're going to be speaking on. The first category I'm going to briefly address is climate changing? Okay? Is there a changing climate, whether it's warming or increasing storminess? And related to that, you can have change that's positive as well as negative. For instance, a lot of people don't know that damaging tornadoes are down 50% since we started monitoring them in the 1950s. Okay, that's the long-term trend, down 50%. You wouldn't know that from listening to the media every time a tornado hits a town, right? Okay, so this is number one. How much is climate changing, and is it good or bad? Number two, to the extent that climate is changing, how much is due to humans? That's something that Nir Shaviv will talk in the second talk. He'll talk about alternative explanations other than CO2, okay, for causing climate change. And then number three is the policy issue, which will be addressed a lot today. How much can we affect climate by changing energy policy? And if we do that, what is the cost versus benefit? A lot of people say, well, we just shouldn't be affecting the climate system at all. And so just as a matter of insurance policy, we need to invest the extra money into not producing CO2 emissions, right? Well, the trouble is it's so expensive and impractical that it's the insurance policy. You wouldn't have an insurance policy on a $100,000 house, let's say a house that costs $100,000. You wouldn't pay $200,000 a year on an insurance policy in case your house burns down, right? I mean, the costs outweigh the benefits. So those are the three categories. How much is the climate changing? Okay. Number two, how much of that change is due to humans? Number three, what can we do about it? And what are the costs versus the benefits of doing something about it? So now I get into my talk. I have relatively few slides. Heartland asked me to cover global temperature monitoring with satellites. We don't monitor surface temperatures, which is where people live. We monitor the troposphere. The troposphere is the lowest part of the atmosphere. If you look at that little red bracket there, it's where all of the weather occurs. It's where 80% of the atmospheric mass resides outside of the tropics. 90% of the mass in the tropics is in the troposphere. And why do we monitor that? Well, for one thing, it's easy to do from satellites. Surface temperatures are much harder. Okay. But also there's a good reason for understanding how the climate system works and whether CO2 is causing warming. And that's because the whole CO2 theory of global warming involves infrared radiation. Okay, that's the energy given off by the Earth to outer space. It's how the Earth naturally cools itself. Okay, and as we add CO2, the theory says we've reduced the ability of the Earth to cool itself by about 1%. That's according to theory, not measurements. None of our satellite measurements of any kind are good enough to measure that. It's a theoretical expectation. So anyway, that infrared radiation, it mostly comes from the troposphere. So it makes sense that we monitor the temperature of the troposphere. Also, it's a more robust signal. The climate models that they run all around the world claim that warming should be greater up in the troposphere than down here at the surface. So it's a more robust signature that we should be able to see. So let's get to what we do with the satellites. For over 25 years now, John Christie and I have been producing a temperature data set. We update it every month of the lower tropospheric temperature and basically the whole tropospheric temperature. They're two different products. And this is a plot since 1979. It's a now over 40-year satellite record that shows how temperatures have changed. Over that 40 years, there has been basically a linear trend upward with a lot of year-to-year variability. But the trend is only 0.13 C per decade. Okay, that's pretty small. You know, that's 1/100 of a degree per year, average warming. Okay, now this is the money slide. That spaghetti plot shows yearly temperatures from 102 different climate model runs, which represent about 24 different climate models, because you can do different runs or different experiments in the same climate model and get a different answer. This has a total of 102 on it. That black line is the average of all the 102 model runs, and this is, again, this is the global average lower tropospheric temperature. This is what we monitor, and which I showed previously here. Okay, this is the monthly stuff from the satellites, global average lower tropospheric temperature variations. Here it's now averaged to yearly, okay? And so that previous slide, that's the blue line. Our UAH satellite data shows the least amount of warming, at least it looks like it on this plot. There's another group called Remote Sensing Systems, RSS, that has their now revised estimate from the satellites, which shows somewhat more warming than we do. That black line is the average of all 102 model runs. That black line represents what energy policy is based on, energy policy changes. It's based on those climate models being correct, okay? Now, also shown on here is the average of 4 reanalyses. Reanalyses are global data sets where they've thrown in all the observations they can find, surface temperatures, weather balloons, commercial aircraft, ships, buoys, a variety of satellites measuring all different kinds of things, and then using physics to sort of estimate, based on all that information, their best guess of what's going on in the climate system. And you can see that those reanalysis data sets agree with the satellites that the climate models are producing too much warming. Compared to our data set, the UAH satellite data set, it's about twice as much warming of the lower troposphere in the climate models compared to the observations. And again, those climate models is what proposed energy policy changes are based upon. Now, if we look at the trends for each one of those curves, there's a linear trend that each one of those curves will have in terms of a warming rate per decade. And I rank them. If I rank them from the warmest on the left to the coolest on the right, this is what we see. The model with the most warming is the NOAA GFDL model. That's the Geophysical Fluid Dynamics Laboratory of NOAA. It's got about 0.4 of a degree C warming per decade. That's at the far left. Then there's 4 Canadian models. Having lived on the border of Canada for many years, I would say that's probably wishful thinking on their part. The rest of the gray bars are all the other 102 models. That black bar in the middle, that's the average of all the models. And then over there on the right, you see this rapid fall off in warming trends. all the way over at the right, the one model that has the least amount of warming and is actually closest to UAH, to our data set, is the Russian model. And then comes the Japanese model, that MRI. The 4 reanalyses are next in the green. Remote sensing systems has the red there. But you see that the reanalyses, again, agrees more with the satellites than with all of these models. You know, it makes you wonder, what are these modelers thinking? And since I will be accused of this anyway, since I'm accused of everything else, I want to point out how well our collusion between Vladimir Putin and UAH worked out here. Notice that we got very close to the Russian model as intended. Okay, now we can do this whole thing again just for the tropics. It turns out the tropics is where you really see the supposed effect of global warming, okay? You might have heard of the tropical hotspot. The tropical upper troposphere is supposed to warm more than just about anywhere based on the climate models. And we see even a bigger discrepancy between the observations and the climate models in the tropics. In our case, 2.4 times as fast. That's how much faster the average climate model is warming compared to the UAH satellite. And you see the reanalyses, that's another observational data set, the reanalyses agree with the satellites. It's not warming as much as the climate models say it should be. And we can do this same ranking the warming trends from all of those curves. Here we see UAH all the way at the right there. The least amount of warming is our data set, and the 4 reanalyses and the Russian model all basically agree on tropical warming being about half or even less than half of the average climate model. This is what our satellite data set looks like for the regional trends. This sort of, at least qualitatively, if not quantitatively, agrees with the surface data that there's virtually no warming at the South Pole, and as you proceed northward, you get more and more warming, with the greatest warming at the highest northern latitudes. And this is what you'd expect for any kind of warming, whether it's human-caused or natural, because as you proceed north from the South Pole to the North Pole, generally, you have more and more land. You know, the southern hemisphere is mostly ocean, northern hemisphere is mostly land. Land warms faster than ocean. So no matter what's causing warming, you expect this kind of pattern. You also expect there to be somewhat more warming over the land masses than the ocean masses for the same reason. So I'm actually going to finish early, give Nir some extra time on his talk, because he needs it. I saw how many slides he had, so. Okay, conclusions. Satellite monitoring of tropospheric temperatures provides an essential check on climate model forecasts. I could tell you a lot more about the reasons why there's a disagreement. We're funded, UAH is funded by the Department of Energy to examine the reasons for the discrepancy between models and observations in the tropics, and we have some answers on that, but that's not what I was asked to talk about today. Clearly, the main conclusion here that's really important for policy is that these models that policy is based on have problems, okay? They're warming too much. Not as much at the surface. That wasn't part of what I was asked, and I hope somebody else will discuss that today. There's more agreement at the surface between models and observations, but if you look closely at the data sets, you'll find that there's an increasing divergence now between the models and the observations in the last 10 or 15 years. Plus, there's some questions about surface data sets, and that will be addressed by someone today. Whether we can even believe the surface temperature data sets. Every time they do new adjustments to them, they come up with more and more warming, as if they're all competing with each other to see who can get the most warming out of their surface data set. Okay, now, just because the observations show half as much warming as the models doesn't mean the models are half right, okay? because the models only produce warming from increasing CO2, and that's the way they were designed. The temperature change in anything, whether it's the climate system, a pot of water on the stove, your body, your car engine, anything, a temperature change is a result of an imbalance between energy coming in and energy going out. All right? Well, for the Earth, we don't know the energy flows in and out of the climate system to the accuracy needed to know whether the climate system is naturally in energy balance. So what the climate modelers do is they program the models with the assumption that there's a balance. In other words, the assumption of no natural climate change. Then they add CO2, and the model warms, and they see, increase, we proved CO2 causes warming. Well, duh, it's what you assumed to begin with, okay? All right, early indications, they're now doing CMIP-6 climate models. What I showed you was everything was from CMIP-5 climate model runs. Earlier indications are that the CMIP-6 models have even more warming than the CMIP-5 models. I don't know why. They're just ignoring the observations. And finally, what I started out with, there is no climate crisis, there is no climate emergency. Even if all of the warming we've seen in any observational data set is due to increasing CO2, which I don't believe it is, it's probably too small for any person to feel in their lifetime. And I'll leave it at that. Thank you.